My name is Susie Shee. I'm a physicist here in the School of Physics at the University of Melbourne. Personally, I work on particle accelerators. I realised I didn't mention that last week, so if anyone has questions for me, let's find that later. Feel free. I'd like to start by acknowledging the traditional owners of the lands on which this lecture is given tonight, the Wurundjeri people of the Kulin Nation, and to recognise the Indigenous peoples of this land as the first scientists as well. So it's an absolute pleasure for us to be delving further into a very recent scientific developments this evening. It's also an enormous pleasure to introduce to you tonight's speaker. Professor Lloyd Hollenberg is an absolute expert in all things quantum computing, and the reason I invited Lloyd to give tonight's lecture was that I had the pleasure of hearing a summary of some of his research work in the School of Physics, and his 20-year expertise in quantum computing has led to the siting of an IBM quantum computing hub at Melbourne. And I thought this is an incredible move. And I also learned within that presentation that we at the University of Melbourne, led by Lloyd, are already teaching students here to program quantum computers. That got me very, very interested, and it kind of blew my mind a little bit. And so in programming this year's lecture series around the theme of quantum mechanics and both its fundamental nature but also its uses in our everyday lives, I thought, well, I absolutely have to have a stellar lecture on quantum mechanics, and so that's why I invited Lloyd to speak this evening. So Lloyd will be speaking on quantum computers approaching fast. And Lloyd, it's a pleasure to have you. Over to you. Thank you very much.
Thank you very much. Hello, everyone.
Hello.
I apologise I didn't turn this on straight away.
Welcome.
Thank you. So let me just get ready here. So, thank you, Susie, for that introduction. A little bit of pressure there. But I was just thinking as I was sitting here before, I've been giving a few of these lectures, and I was thinking back, the first one may have been about 30 years ago. And I don't know if anybody was here for that one. Renewable energy and climate change in the early 90s. Did anybody know? Just looking ahead a little bit. Okay, so tonight I'd like to tell you a little bit about quantum computing. I think over the years I've probably spoken about quantum mechanics and quantum physics and portending the arrival of some interesting science and technology. And indeed, we are here now, quantum computers. They're approaching us very quickly, and they're approaching very fast speeds. We're starting to see that happen. I'd like to tell you a little bit about that tonight. Okay, so this is my favourite place to start when I talk about things quantum, just to put it in perspective. So imagine the visible surface there is a representation of the physical world, and the forefronts of physics are things like the ultimate structure of matter, and as we're seeing a little bit more about lately, the ultimate structure of the universe. And I've been using this Hubble image for quite a while now, and now I can update it. Now that we've got a new telescope up there. Isn't that amazing? Let me just go back, forwards. I've taken this from the NASA site. It's really quite amazing. But quantum mechanics is all about not so much just about what we can see in nature, but the reality of nature. And this is why I like to put it down in the murky depths, that quantum mechanics really underpins a lot of our understanding of the physical world. Where does this sit with respect to tonight's lecture? So in the 20th century, when quantum science was really rocketing along and all sorts of new things were being found out, the associated technology that was developed are things that we use today in our computers, in our phones. The chips are all based on a lot of the quantum science that was developed many decades ago. But what we're seeing now is a different type of quantum technology, and so this is why it's often referred to as a second quantum revolution. And a lot of people, when they hear that, go, wait a minute, what was the first one? Well, that was it. But the second quantum revolution is all about being able to control at the individual quantum level the objects in question and to build new science or new technologies out of these systems. And the sort of things that you may have heard about are secure communications based on manipulating individual photons of light, quantum communications, quantum sensing that we do a lot of here in the School of Physics and across the university. But what I'll be talking about tonight is quantum computing. So using the individual quantum systems that we can control in nature to form bits that represent information and interact to do computations. And this is all based on not just quantum mechanics, but a sort of a merging of quantum mechanics and information science, quantum information. Okay, so it's often predicated by this view of what's happening with computer chips at the moment as they are miniaturized over the decades following this Moore's law. Here I'm plotting effectively the size of a single transistor in one of your computer chips. And we're well into the regime now. We're starting to get to the single atom level, and that's basically the limit of how small you can make transistors. So there's kind of a realization that we're getting towards the end of Moore's law, which was the exponential development of computer chips over the years. Also, even though we can make chips with a lot of transistors on them, they're still not powerful enough to solve certain problems. There are, in fact, many optimization problems and problems in chemistry where even our most powerful supercomputers really struggle. And so this is where quantum computing comes in. If we have a very simple Venn diagram of classically hard problems, classical for physicists just means anything that's not quantum. I can't help using the word. But so hard problems, and within that whole space are easy problems. Quantum computers work on the principle of quantum mechanics and can circumvent some of the limitations of conventional classical computers. And so entering in the Venn diagram is the appearance of quantum computers and their ability to make some very hard problems easy, or in fact easier, and I'll talk a little bit about exactly what that means later on. But basically it's a new part of the Venn diagram where people are now exploring what sort of applications a quantum computer would be able to look at and solve. And these are things that are probably relatively familiar in optimization and finance, AI and machine learning and so forth. It's very exciting how we're just at the time where we're learning how to take a problem and program it into a quantum computer. The question is, are the quantum computers that we have now, or likely to have in the next 5 years or so, going to be powerful enough to solve those problems faster than any conventional computer can? That's really one of the main questions, and it's still pretty much an open question. Okay, so let's just orientate ourselves. So a classical bit that exists in our computer chips is basically a switch that can be on or off and encode 0 and 1. And if you have enough of these lined up, you can encode many zeros and ones, and hence that's a binary number, and that's how we represent numbers in our computers. But these bits can only be either 0 or 1. You can only have one binary number represented in a series of these transistors at any one time. Quantum information, as you probably suspect after hearing a few lectures on quantum mechanics over the years, is very different, and that's what I want to just get across to you now. So I'm not going to go through a whole discourse on quantum mechanics. I'm just going to distill it into 3 dot points on this slide. The important things that you need to know about quantum mechanics in order to get a feeling for what's happening in a quantum computer. So quantum superposition is one of the first things about quantum mechanics that we need to know about. And it's basically, in a nutshell, the combination of effectively zeros and ones existing at the same time. And that's a quantum superposition. And then if you measure such an object, a quantum superposition, you then collapse it into either a 0 or a 1. And it does so at random. But the randomness is something that you can actually control and program in, and that's what we want to do tonight, show you how that works. And then the next level up is when you generalise this quantum superposition over many quantum systems. This is where you get into the realm of quantum entanglement, which is a new level of spookiness, and it's one of the things that Einstein really objected to about quantum mechanics. And it's basically if we have two of our quantum systems that are entangled and you measure one of them, that measurement will dictate what happens to the measurement of another. And we'll go through that as well. Okay, and the solace from Bohr is, don't worry if you haven't really understood any of this. Anybody who claims to have hasn't really understood the first thing about it. So that's always a good place to end up in. Okay, so let's go through those first two bits. All right, so here is a familiar starting point for a quantum object. So it's an atom, and of course we don't believe in the planetary motion model there, but it's good enough for us at the moment. So imagine we have two energy levels for our atom. We have a ground state and an excited state, and we just simply label these as 0 and 1. So this is an electron that can be in a 0 state or a 1 state. Okay, so it's got available these two states. The notation here of the little pointy bracket is just a signifier that we're talking about quantum things. And this notation was invented by Dirac, and we use this all the time now. Okay, so a quantum superposition is where we have that single electron and we put it into an overall state where it's actually a little bit of 0 and a little bit of 1 all existing in this quantum superposition. So it's you can look at it as being in both states. It's in this combination. And because it's hard to describe, I usually just refer to it as a bubble of a quantum state where there's 0 and there's 1 in there. And the thing is, if we do a measurement of that quantum superposition, we effectively collapse it to one or the other, a 0 or a 1. And the appearance of 0 or 1 is completely random. However, we can control the probability of measuring 0 and 1, as we'll see in a moment. And that's really at the heart of what we're doing in a quantum computer. Okay, so imagine that we've created one of these superpositions and we want to do a measurement. Then, as I said, we'll sometimes get a 0 and we'll sometimes get a 1. But imagine we set up this experiment such that we can always go back, repeat and prepare the same quantum state and just do the measurement again, and essentially start counting up how many zeros we get and how many ones we get. Okay, so let's just tally that up and say we did this 100 times, and out of the 100 times we got a 0 60 of those times. Okay, then we would start saying, well, that would mean that we could calculate approximately that the probability of measuring a 0 in this particular superposition that's always prepared to be the same is 60 over 100, or 0.6. And if we got 60 zeros, we must have got 40 ones out of our series of 100 experiments. So the probability of a 1 then is 0.4, and the sum of these should be 1. Okay. So the thing is, how do we know it's going to be 0.6 and 0.4? We can actually set it up in that way. And this is where we need just a little bit of mathematics, if you indulge me. Okay, so when we talk about a quantum superposition, we talk about an overall state which we label as this psi. Okay, that's the overall quantum state that's made up of 0 and 1. And we literally mathematically write it as this sum of a 0 part and a 1 part. And in front of these, we put a little coefficient, a little thing called an amplitude. Now that amplitude is really important because these tell us, if we know what they are, they will tell us what the probabilities are of measuring a 0 or a 1 if we did that experiment. And it's very simple how it works. For the purists in the audience, these are actually complex numbers, but for the moment, don't worry about that. They're just numbers. The square of these amplitudes actually are the probabilities. So if we prepare a particular quantum superposition and we know what A0 and A1 are because we organised our experiment in that way, we can just square them up to get the probabilities. So then it looks like this, what we just did. We prepare a superposition in general, and if we get an outcome 0, what's happened is that the overall state has collapsed to L0, and it does so with a probability that's given by this A0 squared. And conversely for the 1, if we measure a 1, it means that the whole thing has collapsed to just the 1, and the probability of that is A1 squared. So that's the maths. Apologies for that. We can actually do without that, but there'll be a little bit of that to come as well. So let's imagine we prepared a quantum superposition, and we prepared it with the amplitudes that look like this. Okay, so those numbers A0 and A1 now govern the probabilities. If we square them up, they will be the probabilities. And if we did our measurement and we squared up A0, 0.75 squared is 0.6. So in other words, to get the results that we saw in our experiment just before, the 0.6 and 0.4, this is the state that we need to prepare. We know the amplitudes and what they would need to be. And in a quantum computer, it's all about knowing how to do things like that, programming it to do what you need it to do to get the right probabilities. So here for A1, the probability is 0.633 squared, we get 0.4. That's basically the mathematics that quantum mechanics use to describe these states, up to the fact that these are actually complex numbers, but let's not worry about that. Okay, so in any given shot of doing this experiment, we prepare the same state and we know the underlying probabilities now. Okay, so let's start talking about computing. Let's get closer to computing. So you might be aware of a classical logic gate called the NOT gate, which basically takes in a number 0 and turns it into a 1, and conversely, if it's a 1, it flips to a 0. Okay, a quantum logic gate does something similar, but it does it on this superposition. So the corresponding NOT gate in quantum mechanics is actually called an X gate. And what it does is it takes in a combination of 0 and 1. And it operates on both of them. And these bars here represent those amplitudes, A0 and A1. Okay, so they come into this gate. And what the gate does, it flips the 0 to a 1 and the 1 to a 0. So what comes out the other side looks like that. It just flips those 2 bits. So you see it's very different to this object, which only works on 1 bit at a time. So it's basically flipping those. There's a whole series of these gates, as we'll see in a moment. A really important one is called the Hadamard Gate, and it's the one that actually produces these superpositions. So if you have a single 0 coming into a Hadamard Gate, what it does is it produces a quantum superposition. So it generates those quantum effects, and you can see it produces that perfectly even superposition where you get 50-50 chance of seeing one or the other. Okay, so that's enough of the mathematics and everything. What I'd like to do is just show you how this works using a simulator tool that we developed here at the university several years ago now, basically to enable us to teach quantum computing to students from varied backgrounds, not necessarily physics backgrounds, and in a way where we don't get bogged down in too much of that mathematics. So let me fire it up. You can actually, if you have a laptop here, you can just go to qespace.org and run it yourself if you'd like, but let's see if it's all working here. We're not working. I don't like logging into a system in public, but I feel like I am forced to. Let's hope that works. So this was all set up before, but obviously the system went to sleep. So let's see if we can find QESpace. This is how easy it is. Okay, so you come to this website. And you can just go straight to the middle there, QE, and we'll continue as guest. Here we are, here's the system. Okay, so basically what you're looking at, and yes, the mouse is there, I'll go to pointer mode. All right, so you see we have our little zeros here. Each one of these lines across is a qubit evolving in time. Let me just change it to 1 qubit for the moment. Okay, so this is representing a single qubit, that's the line here, and there are time steps here where we can put logic gates, like I showed you, the X and the Hadamard and so forth. If I hit compute now, it's going to run this empty program, and what it does is it actually sends that to one of the computers here on campus. It runs a simulator of a quantum computer and then returns all the data to the browser. So we hit compute and we see our results down here. Okay, so the first thing you see is a little histogram there around the state 0. It's basically saying if I was to make a measurement of this system, then I would measure 0 100% of the time because that's all there is there. Okay, and if I look at the 1 state here, there's no probability of measuring that. Okay, but let me program in that X gate. So I put in an X gate. It gives me a little warning saying that the program's changed, so those results don't correspond to the program anymore. But I hit compute, and what the X gate has done has flipped the 0 to a 1. Okay, so now there's 0 probability of measuring a 0 and 100% probability of measuring a 1. Okay, so that's all well and good. Let's just delete that. Here's the Hadamard Gate. We'll put that in and we'll hit compute. So you see what the Hadamard Gate is, it's taken a 0 coming in and produced an even superposition of 0 and 1. And if you just put the mouse over here, you get the information card that tells you the state is 0, it's got a probability of 0.5. The magnitude of that amplitude is the square root of 0.5, which is 0.707. And similarly for the 1 state. Okay, so we can also program something a little bit more interesting into there. So I've just grabbed, these are the sort of single qubits gates, logic gates that we can have, and a T gate is another logic gate that I haven't unfortunately got time to explain, but it's just another gate. And if I run that program, I've now created an uneven superposition. And so you can see that there's now a probability of 0.854 of seeing this in the 0 state if we made a measurement, and a probability of 0.146 of seeing it in the 1 state. And we can add measurements to see how this all works. If we were to run the experiment over and over, then many times we'll get the 0 state, but occasionally we'll get the 1. Okay? So you can see that we're just getting results commensurate with those probabilities, and now we're not seeing the 1 state. There we go. There it is. So the other thing we can just do for now is to show you what happens if, let me just do a compute on that. Okay, so I've got my state back again. This is an important feature of this program. It allows you to step back through the system itself. Okay, but if I was to put an X gate in here, you can see immediately what's going to happen. The X gate will flip a 0 to a 1 and 1 to a 0. And so if I stop that, it was in a loop. If I hit compute, we swap those results around because we've basically flipped the qubits. Okay, so this is essentially the way that people learn how to program quantum computers. There's a drag and drop system where you can put the gates in. More advanced programmers will have this, but in a text-based version. And so they tend to fire off the quantum circuits, which is what these are called, a little bit more quickly. Okay, so that's just the starting point. Let's go back to the slides. Yes, it does work. We had a little bit of trouble with that, but it seems to be working again. Okay. There we go, jump ahead. Okay, so that was all about single qubits and programming logic gates. What we'd like to do now is to get in touch with computing itself, and we can only do that once we start talking about multiple qubits and how they combine together to form binary numbers. So we're going to have a little bit of binary stuff going on, but let's have a look at what that means. Okay, so what I'd like to get into now is this whole thing of 2 qubits and entanglement and all of that. Okay, so let's imagine we have a 2-qubit register now, and on each of those qubits we do one of those Hadamard gates. So we have an Alice qubit and a Bob qubit. Physicists like to name their quantum systems. So on Alice we do a Hadamard on a 0. This is what this notation means. And a Hadamard on a 0, as we saw, produces an even superposition of 0 and 1. And the amplitudes are the same, and they square up to a half, and each of them then, when you add them up, a half and a half is 1, so that's all good, and the same with Bob. So basically 2 qubits, they don't know about each other, but they're both in a quantum superposition. Okay, so we like to then write down what the overall state of those 2 qubits look like. And it's a little bit more maths, I'm sorry, but it's really just multiplying out these 2 expressions. It's as easy as that. So we have an Alice qubit here, and we have a Bob qubit here. And each of them are in that even superposition. And we literally just multiply them out. So we go a half 0 times a half 0, and that gives us a 1 on root 2 times 1 on root 2 gives us a half, and we get a 0 and a 0. And we do that for all of them, and we get basically a half in front of every possible combination of the 0 and 1. Okay. Physicists tend to be a little bit lazy, and instead of writing that middle bit here, we're just going to get rid of that and write this one as a 0, 0, this one as a 0, 1, and so forth. And you can see now that when we have 2 qubits like this, and we just ask what is the overall state, it looks like a quantum superposition of binary numbers. Okay, so you see here is a binary 0, 0, 0, 1, 1, 0, and 1, 1. And if you remember, 0, 0 is just the binary equivalent of the decimal 0, and 1, 1 is a decimal representation of the number 3. Okay, so these are just now a nice representation of binary numbers in our quantum register. And if we were to ask, okay, if we were to measure both of these qubits now, we would get, say, a result 1 and 0. If we measure Alice to be 1 and Bob's to be 0, we would get that result with a probability 1/2 squared, which would be 1/4 of the time. That's how all this works. Okay, well, it's also interesting then to make the connection with decimal numbers. That's the connection to binaries. So this is what we've just written down, and in the QE system, that's what would be called the binary notation when we look at the information cards. But the way we can represent decimals is the following. 0, 0 is 0, 0, 1 is 1, 1, 0 is 2, 1, 1 is 3, and so forth. And so we could have actually written that in a different way, fundamentally different way, that kind of ignores the fact that we have the 2 qubits there and just treats them as numbers. And so this is now written the same state as a superposition of the decimal numbers, the integers, 0 to 3. And if we ask ourselves, if we measured our register, what's the probability of finding the number 2? That would be 1/4, because we square the 1/2 amplitude. That's how all of this works. Okay, so on the QE, if we were to program in 2 Hadamards there, and just hit compute, we would get this even superposition over all of those 2-bit binary numbers, 0, 0 up to 1, 1. And if you looked at those information cards, you would see that the amplitudes are 0.5 and the probabilities are the square of that, which is 0.25. Okay, so it's not a particularly interesting state, as I'll tell you about in a moment, but it's a very important starting point to have a register that represents a superposition over all the numbers that you can represent with the bits that you have. If you now went to 3 qubits, and now I'm just going to label them not with names but with colours, so we've got A, B, C, and we did the same thing, we multiplied them all out. I hope you can see that what you would get is basically an even superposition of all the 3-bit binary numbers. So 0, 0, 0, which is 0, up to 1, 1, 1, which is the integer 7. Okay, and all of the probability, the amplitudes are this sort of 1 on root 2 cubed, which is 0.3536. So we're getting closer to something that looks like computing. Okay, again, if I was to go onto the QE and put 3 Hadamards there and hit compute, I would get this even superposition. And indeed, you could see from the state information cards what the amplitudes and probabilities are. And now, if I do something a little bit different, if I program in a HTH in the middle, do you remember that was the sequence that gave us that uneven superposition? Then what it produces is this particular state. And the reason it looks like this is if you go back to what we're actually doing, we're only operating on the middle qubit. And I'm sorry for all the complex mathematics here, but it's basically, this is that superposition state with those different amplitudes. That gets put into the middle qubit, but the other ones are left alone. But when we multiply it out to get, say, the 0, 0, 0, we're multiplying in this 0.924 into the 1 on root 2s. And that eventually gets us this 0.213, the probability of those blue ones. And conversely, if we multiply into the second part of this, any of the other ones, we get the lower probability. Okay, this is how you see when you do these operations what the final probabilities look like. And we've done something really nice here. What we've done is put a program in that has adjusted the probabilities of measuring particular binary strings. And that's really important. That's really central to how a quantum computer ultimately works. Okay, so where we are at the moment, we've just been talking about 2 qubits, or well 3, but let's go back to 2. We've put them each independently into a superposition. And what we've noticed is that if we do a measurement on this qubit here, this is the Alice qubit, nothing will happen to Bob because we're not measuring Bob at all. So Alice's qubit collapses to a 0 or 1 and nothing happens to Bob. So this is actually a rather uninteresting state of affairs. This state doesn't actually do a lot. Thank you. But in order to actually compute from this point, we need the qubits to actually interact. And this is where we get to now. And in doing that, this is where we generate entanglement. And in the sense that measurements of one qubit will then be determined by what happened to measurements of a previous qubit, we see that these numbers become somewhat quantumly connected. So the gate that does this, that people often use, is the C-NOT gate, the controlled NOT gate. And the rule is very simple. There's 2 qubits. One is the control and the other one is the target. If the control is in a 0, you do nothing to the target. If the control is in a 1, you flip the target with something like an X gate. So this is what it looks like when we program it. The control qubit has this little filled-in blob here, this dot, and the target qubit has a what is actually a binary add operation, which is equivalent to a flip. So this is signalling that if the control qubit is in a 0, we do nothing. If it's in a 1, we flip this one. And so the truth table is 0, 0 goes to 0, assuming that the first qubit is this control. The only things that happen are here, where the first qubit is in a 1, that signals that the second one has to flip from 0 to 1. And this one here, where the first qubit is in a 1, it means that the second one has to flip to a 0. So that's what happens in this C-NOT gate. But it does this in a quantum way. It does this over a quantum superposition. So if we were to present this C-NOT with a superposition over 2 qubits with amplitudes A, B, C, D, which we'll just don't worry about for now, what it does is it acts on every part of the superposition in parallel, does that all in one go. And if the first qubit is the control, the first 2 bits don't change because it's in a 0, but the second 2 bits do, parts I should say. And what we've seen is the 1 0 goes to a 1 1 and the 1 1 goes to a 1 0. And another way to see that is in this diagram. If a CNOT gate is presented with some quantum superposition of the binary numbers, it goes to a new superposition where these parts here have exchanged amplitudes. So this is how a CNOT gate works, and this is the thing that interacts our qubits, our bits, and hence is part of how we process information and do mathematics in our quantum computer. Okay, so I can't get to this point without talking about entanglement. And as I said, this is the stuff about quantum mechanics that really bothered Einstein. And at the nub of it is the following. So you imagine that we have our 2 qubits and we put them into this superposition where we independently had Alice and Bob in their superpositions that we created with Hadamard gates. We saw that the measurement results on Alice and Bob are completely independent, because if we measure Alice, Bob doesn't know about it, and so it's still in a superposition. But imagine we have a state that looks like this. It actually looks a lot simpler than this one here because it's got fewer parts to it, but it's actually far more complicated. Well, I should say probably interesting, because now the measurement results are actually dependent on one another. But what happens to a measurement on Alice will affect what happens to Bob. And we see that in the following way. So just out of curiosity, this is what's known as a Bell state, after John Bell, who really worked out how you start to design experiments to really test out these aspects of quantum mechanics that so bothered Einstein very much. Okay, so let's have a look at this state and let's pick out the first qubit, the Alice qubit, those parts of this, and we do a measurement. So obviously there's 2 possibilities, excuse me, for Alice, 0 or 1. So because the amplitudes are 1 on root 2 and they square to 1/2, those 2 possibilities of measuring Alice as a 0 or 1 will occur 50% of the time each. So imagine Alice measures 0. The whole thing then collapses to a 0, 0 part. We've actually extracted this part of it. And so if Bob comes along now and does a measurement, he has no choice but to get a 0. And similarly, if Alice measured a 1 from this, the overall state would collapse to 1, 1. And if Bob came along, Bob would also have no choice but to also measure a 1. So Bob's measurement is completely dependent on the outcome of Alice's measurement. So it's very different to the other state where those measurements were independent. So obviously you can see why this bothered Einstein, because if you separated these 2 qubits to either end of the galaxy and did the same experiment, how would Bob's qubit know which result to be in? That's basically the nub of what's known as the EPR paradox. But this is the way the world works, and it's proved again and again in the quantum computers and the physical systems that we measure. And it was John Bell who really figured out how to test that out. Anyway, so back to computing. So the way we generate such an entanglement in a quantum computer is to just have a Hadamard gate on our first qubit and a CNOT gate on our second one. And in doing so, if you chase it through, you'll see that what you produce is the 0, 0 plus 1, 1, and you can see that there. In our QE system, this slider bar that runs backwards and forwards has now turned red, signalling that you've generated entanglement. And in fact, it's very red. It's at the maximum of the entanglement scale. It's the maximum entanglement you can generate with 2 qubits. Okay, so let's now, with all of that, look at what quantum information processing actually is. So basically, there's a bunch of logic gates between our qubits that perform mathematical operations on the binary data, things like Hadamard, CNOT, and a bunch of other gates you saw in the QE system. From those gates, we create very complicated entangled states, and the binary data encoded in our computer in that vast quantum superposition is linked. And then a very important part of all of this that we kind of saw with that HTH sequence, the program that we have on our quantum computer is basically interfering the amplitudes. Because after all, quantum systems are behaving like waves, and so those amplitudes are actually things that can interfere like waves, and hence we can adjust the probabilities of one particular outcome over another. So put it another way, if we started our quantum computer in this superposition over all 4-bit states, all 16 of them, and we implemented some quantum algorithm, this is our program now of a whole bunch of different gates, we see that we're adjusting the probabilities of the outcomes. And another way to look at this is as a function of time going backwards in this forest of probability peaks, and along here, if these represent the peaks correspond to particular binary numbers, we see that in time those peaks change in height. And what the quantum algorithm is doing, it's sifting through all of those amplitudes, interfering them in such a way that the probability of a particular binary string, which represents the answer, has a much higher probability of being measured when you read out than anything else. That's what a quantum computer is doing. It's adjusting probabilities of these numbers in such a way that the answer to the problem is vastly higher in probability of measuring out than anything else. That's essentially what a quantum computer does. So let's go right ahead now to an actual algorithm. And a very famous one is the quantum search algorithm. And I'm going to pose the quantum search problem like this. So imagine you have an alphabetical phone book. All right, so normally you just look up the name because it's already ordered alphabetically. But your task is you're given the number and you're told to find the name. Okay, so that's now really hard because it's ordered alphabetically, not according to the number. So you now just have to randomly go through that phone book until you find the particular number and hence the name. And if you're doing this classically, and the phone book has n entries, it would take you on average n on 2, whether it's in the start or at the end, if you were to do this many times. The quantum search, Grover's algorithm, does this in far fewer lookups. In fact, quadratically fewer. It goes like root n. So what's Grover's algorithm doing? Well, let's just pose the problem that our database is all of the 8 3-bit numbers. Okay, and we want to search for a particular number in that database. So say the number 5, which in binary is 101. Then we now know how to create the database. So we will have a database that looks like this in our quantum computer. It'll be an even register. And we'd like to identify the number 101. So that's our search problem. If we just stopped here and looked at what the probabilities are, it's basically 1/8 to measure any of these binary strings at this point in the quantum computer, which doesn't help us because on average it would take us, sort of 8 times thereabout to actually find the right one. So that doesn't help us. That's still in classical land. What you need is an algorithm that manipulates the probabilities. And this is what Grover's algorithm does. It manipulates the amplitudes so that at the end of the algorithm, the probability of finding our particular string that we're searching for is much higher than anything else. And so while people often say that a quantum computer is looking at every part of the haystack for the needle at one time, it's actually not really doing that. What it's really doing is amplifying the size of the needle to make it easier to spot. So this is the program that you would need to do that. So if I have got time, yes, I think we might. Yep, okay, let's have a look at programming that in the QE. All right, so the first thing we'll do is go to 3 qubits. Go to pointer, get rid of all of that. Okay, so we want to create our database. So we put 3 Hadamards there and we create our superposition and all the probabilities are even. And now what I'm going to do is create what's called the oracle. So we're searching for a particular state and we want the program to tag that state. And we do that as follows. So we need something called a Z gate here. So just bear with me. So this is basically a gate that says when both the first and the second qubit is in the one state, apply what's called a Z gate here. And unfortunately, we haven't got time to explain that, but I can go through that afterwards if people would like. So this is called the oracle, and if I hit compute there, I can see what it's done. It's actually, I've programmed it to identify the 101 state. Okay, and it's done that by changing its amplitude. The probability is still the same, but you see what it's done? It's turned it red, which in the QE means it's given it a minus sign. Okay, so that still doesn't help us, but what we can do now is to make the amplitudes, let me just do copy paste. We want to make the amplitudes interfere with another little program snippet, which I'll put in here. This is called the inversion step. And mathematically what it's doing is it's calculating the new average of amplitudes and then reflecting around that average. But if that doesn't make sense, we just hit compute and we see what's happened. So everything that wasn't tagged has done the same thing, except for the state that was tagged. And it's all done this in a certain way so that anything that wasn't tagged by the oracle here has a very low probability now. And the state that was tagged, 101, has a much higher probability of being measured. And in fact, I can just do a copy paste, do that a second time, and you see another iteration of that has amplified that effect yet further. So all the probabilities of the states we don't want to see have gone down, and the state that we do want to find has gone up. And you can see if we go back through the program with our slider there, we see the oracle tags the state. This little code snippet does that reflection and manipulates the amplitudes. And then we do the same thing again. We now tag this state, our search state, to be different to everything else. It's a different colour. And hence, when we go through that second iteration of the inversion, it amplifies that dampening of all the probabilities except for the one that we want. So this is basically how quantum computers work. And in the time available, I'll just say a little bit about where quantum computers are and where they're going. So let's have a look at what would happen if we did this on an actual quantum computer. So QE is running a simulation of an ideal quantum computer. So this is what the program looked like on the QE system. But if we were to go to one of the IBM quantum systems and program it in, you can see it looks very similar. There's some technical differences, don't worry about that. We pick a particular quantum computer to run this on called Vigo, which the open means that if you were to just register for IBM Quantum, you could do exactly the same experiment as I'm doing here. This program is then compiled or transpiled to a circuit that can actually run on the computer. It actually makes it longer. And then at the end of the day, if we simulate it on the IBM Q simulator, we see that it looks exactly like the QE output here, except if we actually run it on the quantum system, what we get is this. So it actually looks similar, but we see now that our amplitudes, probabilities of our non-search states have actually crept up. It looks vaguely the same, but what's happening here is all the logic gates have a little bit of noise associated with them because quantum information is very fragile to anything happening in the environment. And so this is basically one of the main things that stops us from solving big problems on quantum computers that are coming out. The fact that the noise affects the relative relative probabilities. So the big job at the moment is to work out how to reduce that noise and how to run algorithms, design algorithms that are more impervious to noise. Let me just go ahead a little bit. So one of the things that we've done here at Melbourne University, because we established a IBM Quantum Hub here in 2018, which means we have access to the latest and greatest IBM quantum computers, which is absolutely amazing for us. Gary Mooney and Greg White, two PhD students, have done some amazing work where they showed how to not only create these really highly entangled states called GHZ states on a quantum computer, but to actually verify. And there's a bit of a race around the world to make the biggest GHZ state. And what we're able to achieve on the IBM devices was a 27-qubit GHZ. Not just produce it, but to actually verify it. And further than that, on their largest device at the time, 65 qubits, the largest is now 127, we were able to show the creation of a state that entangled that whole device. Okay, so the types of computers that we're seeing coming out, at the moment they're called noisy intermediate scale or NISC devices. And these are devices in the sort of 10s to, well, we're at the 127 regime now, but they're noisy and they don't have the high level of quantum error correction that we currently need. Although there are lots of problems that we might be able to run on those systems. So at the moment it's all about being able to mitigate the noise on those devices to run the problems we want to run. In the long term, we're talking about many thousands or millions of qubits in fully quantum error corrected systems, and there's a huge class of problems that will see polynomial to exponential speed up. So where are we at the moment? This is nearly at the end. There's been some amazing demonstrations in the last few years that you may have heard about. The first one was in 2019 from Google. And they had a quantum computer called Sycamore that had 53 qubits, and they basically programmed a random program in that quantum computer. And obviously you could now think, okay, if I have the QE and I program a random program, then I'll get some probability distribution at the end. The task, the problem, was to find out what that probability distribution is. So if you have a quantum computer and you program it with the random program, then you just have to measure it many, many times to work out what that probability distribution is. It's like putting a measurement gate on the QE and just hitting it a gazillion times. The other way to do it is to take a supercomputer, in this case IBM Summit, and simulate that quantum circuit. And then to run that simulation so that you calculate what those probabilities are by knowing how to simulate. And so that was the benchmark test where Sycamore got data in minutes that would take the IBM supercomputer 2.5 days. So that's a first articulation really of a non-trivial degree of quantum advantage, or what they call quantum supremacy. A year later, from the University of Science and Technology in China, they demonstrated a photonic quantum computer. Google and IBM's quantum computers are made of superconducting qubits. This one is photonic. And they did a similar problem. It was called the Gaussian sampling problem, boson sampling problem. Basically, running that sampling problem to get the probability distribution out on the actual quantum computer versus simulating it. And they estimated that the data that they achieved in just a few minutes on their photonic quantum computer would take the world's #1 supercomputer, Fugaku, 600 million years. Obviously, that hasn't been proved yet, if that's actually right, but that's an extraordinary statement. And we're seeing roadmaps coming out. This is the one from IBM where they're currently at 127 qubits, and by 2023, they're predicting chips of over 1,000 qubits that we'll have access to, so we're very excited by that. And because we're an IBM Quantum Hub, we have access to that technology, and at the moment we play around with this machine, which is 127 qubits, the IBM Washington machine. So the big open question, as I posed very early on, is whether we can achieve quantum advantage on real-world problems. And that is all about taking machines like this and eking out the advantage, trying to work out how you mitigate the appearance of noise and do that in a way that it's not just dependent on how the hardware is improving, but also how you actually run your programs and how you design your algorithms. So I'm going to stop there. This is our wonderful group working across both quantum sensing and quantum computing. Because I've concentrated on quantum computing today, I've just underlined all of those people there. So thank you very much.
Incredible. Am I on? Yes, great. Absolutely incredible work. Thank you so much.
Thank you.
I've learned an awful lot in 1 hour, or just under 1 hour. And I'm sure you'll have to. Now, while that's processing through your brain, we do have a couple of minutes for some questions, and I'm sure there are going to be many questions for Lloyd. I might kick off actually, if that's all right. So in terms of what a quantum computer would look like in the future, there are clearly competing technologies. You mentioned photonic technologies, you mentioned superconducting technologies, probably other things. I remember, historically, when computers were first invented, the idea was, well, there would be one, there would be a research institute somewhere. And it looks like we're heading towards that phase with quantum computers. Which technology, it might be like choosing baby children, but like which technology do you think, at the moment at least, looks like it might have an advantage, if any? And do you think we're all going to end up with quantum computers, in our pockets?
So I never like the which one is going to win the race type question. But at the moment, we see it's all to do with the fundamental qubit and what it is and how big it is. So IBM and Google's systems are these superconducting systems. The actual quantum computer is probably invisible. It's right down here as a very small chip. But what's required here, this is basically what goes into a cylinder, which is a dilution refrigerator, and keeps it down to just a few millikelvin. And all of these are the wires and circuitry that come out to control the individual qubits and how they interact. So these systems tend to be quite large, and one of the limiting factors is ultimately how many of these superconducting qubits you can fit on a chip when you want millions of them, but also how big a volume can you cool down and have all this circuitry. And so there are really interesting engineering problems to overcome and also quantum engineering problems to overcome. And then there are systems which I've been associated with quite a while through my work in the Centre for Quantum Computation and Communication Technology, which is based on individual atoms in silicon. And they're wonderful systems because they remain coherent for a very long time, but because they're atoms, to get them to interact, you have to put them very close together. And there the challenge is that the systems are just too small. And so you have to have a way of putting them further apart in such a way they can still interact in order to get the wires down, because if they're only 20 or 30 nanometers apart, it's very difficult to get enough wires down to control these systems. So there's this really interesting interplay of dimension of these qubits and the ultimate size of the machines. There are other ones that are based on photonic qubits, and there it's a different problem altogether. They're incredibly coherent. I believe the photons from the early universe still are quantum coherent, whatever that means. But they're very fast. They move around. They're not like individual atoms in a solid that stay still. And so there the challenges are timing, making sure that you're not losing photons and all the rest of it. So the form of quantum computing itself is very different to what I've been showing you, which is based on static qubits and individual gates. There's a huge amount of innovation going on here and a huge amount of inventiveness to basically look at the different physical systems and how they would be built into a quantum computer.
Incredible, and I imagine our students today are going to be having careers that we just can't even imagine.
Oh, absolutely. Yep, absolutely.
I'm going to put out to the audience if there's more questions up there. Give me a second to get your hand up and then choose. I think over this side, I'm just going to run the microphone up to you.
Thank you, Professor, for such a beautiful and clear presentation. I'm a complete beginner in this topic.
Did it make sense?
Probably a very silly question, but are gates actually physical structures, or are they programs?
Very good question. So it's a bit of both. So the qubits are obviously physical. In order to, even on a single qubit, change its state, we have to do something to it. And so that typically could be shining a particular pulse of light on that qubit. And so there the gate is not just the qubit, but also all of that, you know, the laser and all the technology that you need. And similarly, when you interact qubits, then you need some sort of physical interaction. Sometimes it's done by a physical structure itself, or it's done via the natural interaction that occurs between, say, electrons in atoms. So it's actually a really non-trivial question whether a gate is physical or not, because it requires all this physicality of the device structure itself, but also a lot of temporal stuff that's going on, the control that goes on in order to affect the gate, the logical gate that you want. So it's a very good question.
I had exactly the same question, so thank you for asking it. And I am a physicist, so yeah, just here.
Thank you, Lloyd. That was fascinating. I was just wondering about probabilities. So when you were showing those examples, then you get roughly 80%, roughly 90% if you do it with another manipulation. How many times do you have to observe or measure to get the average?
No, that's a really good question, and we kind of saw this a little bit here. So let me go back to this one. So on the QE, you see that the probabilities are perfectly flat, and that's because the QE is calculating the exact probability as a byproduct of how it simulates. Another way to say it is, if I were to put measurement gates here and start measuring many, many times, I would need an infinite number of measurements to reproduce the QE probabilities. But here, when we run it on a simulator that's more like how you would run it on a quantum computer, here is 1,024 shots. So we've done it that many times, and you see that the probabilities aren't perfectly flat, and if you could get close enough, you'll see these percentages are just a little bit different. And that's because we've limited ourselves to 1,000. If we had 10,000, it would be a better estimate, and the accuracy of the estimate goes like 1 on the square root of the number of shots. So the answer is, if we wanted to observe this particular state in with an acceptable probability, then that would be fine, 1,024 shots. When we do it on the actual quantum computer, we see, well, you can't see it, but the probability went from 78% down to about 42%. So the appearance of these other peaks now, even though we have 1,024 shots, that shot noise, which was only at the sub 1% level, is not as serious as the noise that's occurring due to the logic gate errors. So these things, there's two effects actually coming in play there.
Great. Now, I can see that there were more questions, but for the sake of time, because we're a little bit over time already, I think if Lloyd's available...
oh yes, I'm happy to stay back.
Chat to him down front and
Yep, I'll pop the mask on.
Yeah, with the mask on, if we could ask that would be great. Just to finish up for the night, Lloyd, thank you for a fantastic lecture. Could you give him another round of applause and thank you?
Thank you, everyone. Oh, wow. Home will be happy.
Next week we'll have a class from Monash University, speaking on quantum chemistry, which is going to be also really fascinating on how you scale up quantum physics to the largest systems. So thank you all.